So if you stand in the Khasi Hills in northeastern India during the month of June, you'll experience something that's, well, it's practically incomprehensible.
Oh, yeah, it's
Right,
intense.
it's like 13 feet of water just falling from the sky. It's a deluge of biblical proportions.
It truly.
But then, if you drive just a few hundred miles to the west, you end up in the bone-dry, blistering sands of the Rajasthan desert.
Where, an entire year might pass without a single meaningful drop of moisture.
Exactly. And today, for this deep dive, we are unpacking a geographic text that explains the single, massive, invisible planetary engine that is responsible for both of those extremes.
Yeah, we're looking at a machine that is composed of thermodynamics, fluid dynamics, and the actual rotation of the Earth itself.
It's wild.
Mhm.
And the sheer scale of this atmospheric engine dictates not just the physical landscape for you, but the survival, the agriculture, and the culture of over 1 billion people.
It really does. We are basically going to decode the master blueprint of the Indian monsoon today.
And to give you the clearest possible picture of how these geographic mechanisms interlock, we're taking a special approach for this deep dive.
Race something a little different.
Yeah, I am going to present the source material exactly as it was written, reading it step by step, and then we'll pause.
And we'll tear into the physics, the planetary levers and the profound implications hidden beneath all those dense geographical terms.
Exactly. Okay, let's unpack this. The text begins by laying the absolute foundation of atmospheric science. It says, in the last 2 chapters, you have read about the landforms and the drainage of our country.
Mm-hmm.
These are the 2 of the 3 basic elements that one learns about the natural environment of any area. In this chapter, you will learn about the third, that is, the atmospheric conditions that prevail over our country.
Setting the stage.
Right. It goes on. Why do we wear woolens in December, or why it is hot and uncomfortable in the month of May, and why it rains in June, July? The answers to all these questions can be found out by studying about the climate of India.
Which is what we're doing.
Exactly. Now here's the crucial definition part. Climate refers to the sum total of weather conditions and variations over a large area for a long period of time, more than 30 years.
Right. 30 years is the key metric there.
And then it says, weather refers to the state of the atmosphere over an area at any point of time. The elements of weather and climate are the same, i.e., temperature, atmospheric pressure, wind, humidity, and precipitation.
Okay, let's pause there for a second. The critical distinction to establish right out of the gate is the mathematical relationship between weather and climate.
Because people confuse them all the time.
All the time, yeah. We often conflate the two, but geographers view them through entirely different temporal lenses.
Like different time frames entirely.
Exactly. Think of weather as daily stock market volatility. A stock might plunge today because of a bad earnings report.
Or spike tomorrow because of a new product launch.
Exactly. That chaotic, immediate fluctuation that is your weather. It's what's happening outside your window right now.
Right. And climate.
Climate is the 30-year index fund performance. It smooths out all that localized noise to reveal the underlying structural trajectory or the personality of the environment.
So weather is your mood today, but climate is your overall personality.
That is a perfect way to put it.
Okay, so the text goes on to talk about the elements that make up both. It says, you may have observed that the weather conditions fluctuate very often, even within a day.
Which we definitely all notice.
Right. But there is some common pattern over a few weeks or months, i.e., days are cool or hot, windy or calm, cloudy or bright, and wet or dry. On the basis of the generalized monthly atmospheric conditions, the year is divided into seasons such as winter, summer, or rainy seasons.
So both of those things, the daily mood and the long-term personality, they're driven by the exact same underlying variables.
The temperature, atmospheric pressure, wind, humidity, and precipitation.
Yes. But rather than just listing them, let's actually look at the mechanical relationships between them because they feed into each other.
Like a loop.
Exactly like a loop. The primary driver is temperature, which dictates atmospheric pressure. And pressure is literally the physical weight of the column of air above you, just pressing down on the Earth's surface.
Oh, wow. So air actually has weight that we can feel.
It does. And when the sun heats the ground, the air above it warms up. And what does warm air do?
It expands and rises, right? Like a hot air balloon.
You got it. It expands, becomes less dense, and rises. That creates a deficit of air at the surface, which we call a low pressure zone.
Okay, makes sense.
Conversely, cold air is dense and heavy, so it sinks, and that creates a high pressure zone.
And nature abhors a vacuum. Right. It demands equilibrium.
Yes, exactly. So that heavy, high-pressure air rushes across the landscape to fill that low-pressure void, and we feel that rush of air as wind.
Okay, so temperature creates pressure differences, and pressure differences create wind.
Spot on. And as that wind travels, it acts as a giant conveyor belt carrying humidity, water vapor from over the oceans.
And then that becomes precipitation.
Right. When that moisture-laden air is forced upward and cools down, the vapor condenses and falls as precipitation, rain, snow, hail.
So these five elements are just locked in this continuous thermodynamic loop.
Basically, yeah. And when you average that loop out over months, you get the recognizable patterns that we call seasons.
Okay, let's see how those localized loops scale up to define an entire subcontinent.
Let's do it.
The text moves from this baseline to the overarching classification of India's atmosphere. It reads, "The world is divided into a number of climatic regions. Do you know what type of climate India has and why it is so?" We will learn about it in this chapter.
Spoiler alert, it's the monsoon.
Right. The word monsoon is derived from the Arabic word masim, which literally means season. Monsoon refers to the seasonal reversal in the wind direction during a year.
Okay, I want to jump in right here. The etymology of monsoon is so vital because it corrects a really widespread misconception.
Right, because people hear monsoon and immediately picture torrential rain, like just flooding.
Exactly. But the Arabic root mausim simply means season. Scientifically speaking, the monsoon is defined purely by wind mechanics. It's a massive 180-degree seasonal reversal in wind direction.
So it's not actually about the rain itself.
No, the rain is just a byproduct of where that wind happens to be coming from at that time of year.
That's fascinating. Let's keep reading. The text says climate. The climate of India is described as the monsoon type. In Asia, this type of climate is found mainly in the south and the southeast. Despite an overall unity in the general pattern, there are perceptible regional variations in climatic conditions within the country. Let us take two important elements, temperature and precipitation, and examine how they vary from place to place and season to season.
And here's where it gets really interesting with these massive contrasts.
Oh, absolutely. Listen to this. In summer, the mercury occasionally touches 50 degrees C in some parts of the Rajasthan desert, whereas it may be around 20 degrees C in Pahalgam in Jammu and Kashmir.
So for context, 50 degrees Celsius is incredibly hot. It's about 122 degrees Fahrenheit.
It's barely survivable.
Right, human physiology starts to shut down at those temperatures. Meanwhile, Pahalgam is sitting at a really pleasant 68 degrees Fahrenheit in the same country, in the same season.
And winter is just as wild. The text says, on a winter night, temperature at Dras in Jammu and Kashmir may be as low as minus 45 degrees season. Thiruvananthapuram, on the other hand, may have a temperature of 22 degrees C.
So you have places that are freezing to death, minus 45 Celsius, while a coastal city in the south is at a totally comfortable 71 degrees Fahrenheit.
It gets even crazier. In certain places, there's a wide difference between day and night temperatures. In the Thar Desert, the day temperature may rise to 50 degrees C and drop down to near 15 degrees C the same night.
Now, this day-to-night temperature swing in the Thar Desert is perhaps the clearest demonstration of atmospheric physics in action.
Because it's dropping from, 122 Fahrenheit down to about 59 Fahrenheit in a matter of hours?
Exactly, a massive 35 degrees Celsius plummet. And the mechanism behind that is the total, complete absence of atmospheric moisture.
Because humidity usually acts like a blanket, right?
You got it. Humidity is a greenhouse blanket. Water vapor traps the infrared radiation that's bouncing off the earth and keeps the night air warm.
But in the desert?
In the Thar Desert, the air is bone dry. There's no blanket. So the moment the sun dips below the horizon, all that intense heat absorbed by the sand just radiates directly out into space, completely unimpeded.
That is wild. The text then contrasts that, saying, on the other hand, there is hardly any difference in day and night temperatures in the Andaman and Nicobar Islands or in Kerala.
Because there, the humidity and the proximity to the ocean just lock all that thermal energy in place.
Which brings us directly to precipitation. The text says, let us now look at precipitation. There are variations not only in the form and types of precipitation, but also in its amount and the seasonal distribution. While precipitation is mostly in the form of snowfall in the upper parts of Himalayas, it rains over the rest of the country. The annual precipitation varies from over 400 centimeters in Meghalaya to less than 10 centimeters in Ladakh and western Rajasthan.
Again, just unfathomable extremes. 400 centimeters is over 150 inches of rain, while Ladakh gets less than 4 inches for the whole year.
It's basically a different planet. So how do human beings actually adapt to these brutal thermodynamic realities.
Well, it changes everything about how they live.
Exactly. The text transitions into the architectural consequences. It reads, most parts of the country receive rainfall from June to September, but some parts, like the Tamil Nadu coast, gets a large portion of its rain during October and November.
Right, which is an anomaly we'll get into later.
In general, coastal areas experience less contrasts in temperature conditions. Seasonal contrasts are more in the interior of the country. There's decrease in rainfall generally from east to west in the northern plains.
Okay, we are seeing the concept of continentality introduced here.
Continentality, what's that?
It's the idea that the farther you move from the ocean, the more volatile your temperature extremes become.
Because water acts as a buffer.
Exactly. Water has a massive specific heat capacity. That means it requires an enormous amount of energy to change its temperature compared to rock or soil. So the ocean acts as a giant thermal flywheel, stabilizing the climate of coastal areas.
And inland areas just have no such buffer.
None at all. They heat up fast and cool down fast.
That makes total sense.
Yeah.
Now, the text poses some direct questions about how this affects people's lives.
Mm-hmm.
It says, these variations have given rise to variety in lives of people in terms of the food they eat, the clothes they wear, and also the kind of houses they live in.
Which is so true.
And then it asks three specific questions. Why the houses in Rajasthan have thick walls and flat roofs? Why is it that the houses in the Terai region and in Goa and Mangalore have sloping roofs? Why houses in Assam are built on stilts?
Okay, let's break those down, answering them using the physics we just learned.
First, why do houses in Rajasthan have thick walls and flat roofs? If we apply the thermodynamics, the thick walls aren't just about providing shade, right? They utilize thermal mass.
Precisely. Think about it in a desert where the ambient temperature reaches 50 degrees Celsius. A thin wall would just transfer that heat immediately into your living space.
Which would turn the house into an oven.
An absolute oven. But thick adobe or stone walls, they absorb the sun's thermal energy slowly throughout the entire day, delaying its transfer.
So by the time the heat finally penetrates all the way through the wall, night has fallen.
Exactly. Night falls, the outside temperature plummets to 15 degrees, and now those walls act like a radiator, radiating that trapped heat inward to keep the occupants warm.
That is brilliant ancient engineering.
It really is. And the flat roofs. That's simply an acknowledgement of the precipitation deficit. With less than 10 centimeters of rain annually, there's just no need to engineer water runoff.
Right, you don't need a sloping roof if it never rains. But if you travel down to Goa or Mangalore, the text asks why houses there do have sloping roofs.
Because those regions sit directly in the path of the monsoon winds moving off the ocean. They are inundated with staggering volumes of water.
So a flat roof would just become a swimming pool.
A very dangerous swimming pool. If you utilized a flat roof design there, the sheer hydrodynamic weight of that pooling water would cause a catastrophic structural failure. Sloping roofs use gravity to instantly shed that kinetic load.
Makes perfect sense. And the last one, why are houses in Assam built on stilts?
Well, Assam is in the northeast near Meghalaya, which, as we read, receives over 400 centimeters of rain.
Oh, right, the 150 inches of rain place.
Exactly. With that massive volume of water being funneled through the river valleys, severe flooding isn't just a possibility, it is an absolute certainty.
So if you build on the ground, you're going to lose your house every year.
Yeah. Elevating the structures on stilts is literally the only way to coexist with the hydrology of that region. It's a brilliant illustration of how cultural and architectural evolution is entirely downstream of atmospheric physics.
I love how connected that all is. So if these are the localized effects, the houses and the daily temperatures, what are the planetary levers actually pulling the strings?
That is the big question.
The text introduces the master control board of the global climate. Let's read this section. Climatic controls. There are 6 major controls of the climate of any place. They are latitude, altitude, pressure and wind system, distance from the sea, continentality, ocean currents, and relief features.
Okay, so these 6 controls, if we connect this to the bigger picture, they represent the operating system of the entire Earth's climate.
Let's go through them one by one. The text says, due to the curvature of the Earth, the amount of solar energy received varies according to latitude. As a result, air temperature generally decreases from the equator towards the poles.
Right. So the first one, latitude, is purely geometric. Because the Earth is a sphere, solar radiation strikes the equator at a perpendicular 90-degree angle.
It's like a flashlight pointed straight down.
Exactly. It concentrates maximum energy into a small surface area. But as you move toward the poles, the curvature means that same beam of sunlight hits at an oblique, slanted angle.
So it spreads out over a larger area.
Yes, spreading its energy over a much wider area and passing through more atmosphere, which scatters the heat. So, equator hot, poles cold.
Got it. Now for the second one, altitude. The text reads, as one goes from the surface of the Earth to higher altitudes, the atmosphere becomes less dense and temperature decreases. The hills are therefore cooler during summers.
Which we all sort of know intuitively you go up to the mountains to cool off.
Right, but I want to push back slightly on this. The text simply says the atmosphere becomes less dense and temperature decreases. But intuitively, as you climb a mountain, you're getting physically closer to the sun. Why does it actually get colder?
Oh, it's a great question, and it confuses so many people. It comes down to how the atmosphere is actually heated in the first place.
It's not heated directly by the sun.
No. The sun's shortwave radiation doesn't heat the air directly. It passes right through the transparent atmosphere and heats the Earth's surface.
Oh, the ground.
Right. The ground heats up, and then the surface emits long-wave thermal radiation, which heats the air from the bottom up.
Oh, wow. So the ground is the heater, not the sky.
Exactly. So when you are at sea level, you are at the bottom of the atmospheric pool, surrounded by dense air molecules that trap all that radiating heat.
And as you ascend a mountain,
Two things happen. First, you are physically moving away from the massive radiant heater of the lower landmass. Second, the air pressure drops, causing the air to expand.
an expanding gas cools down.
Yes, a principle in physics known as adiabatic cooling. The thin air up there simply lacks the molecular density to retain thermal energy, so it's cold.
That makes perfect sense.
Okay.
That leads directly into the third control, pressure and wind systems. The text says, the pressure and wind system of any area depend on the latitude and altitude of the place. Thus, it influences the temperature and rainfall pattern.
Right, the temperature differentials caused by the first two controls create the high and low pressure zones we discussed earlier.
So the atmosphere basically acts as a giant heat engine.
Using wind to constantly try and redistribute energy from the hot equator to the cold poles?
Okay, control number 4. The sea exerts a moderating influence on climate. As the distance from the sea increases, its moderating influence decreases, and the people experience extreme weather conditions. This condition is known as continentality, i.e. very hot during summers and very cold during winters.
And we already break that down through the specific heat capacity of water acting as a thermal buffer, right?
Yeah, that's the Rajasthan versus Kerala contrast. Then we hit control number 5, ocean currents. Ocean currents, along with onshore winds, affect the climate of the coastal areas. For example, any coastal area with warm or cold currents flowing past it will be warmed or cooled if the winds are onshore.
This adds a massive feedback loop to the system. Ocean currents are essentially vast, submerged rivers transporting thermal energy across the entire globe.
And onshore winds are winds blowing from the ocean toward the land.
Exactly. If an onshore wind passes over a warm ocean current, it absorbs immense heat and moisture. It then delivers a humid, temperate climate to the coast.
Well, what if it passes over a cold current?
If it passes over a cold current flowing from, say, the Arctic, it chills the air. Cold air can't hold moisture, so it condenses and drops its rain over the ocean before it ever reaches land.
Leaving the coastal air cold and completely dry.
Precisely. Which sets up the final control perfectly.
Yes, the final control, which dictates where water physically falls. The text explains it along with a really fascinating geographic puzzle. It says, why most of the world's deserts are located in the western margins of continents in the subtropics.
A very specific puzzle.
Very. It continues, finally, relief too plays a major role in determining the climate of a place. High mountains act as barriers for cold or hot winds. They may also cause precipitation if they are high enough and lie in the path of rain-bearing winds. The leeward side of mountains remains relatively dry.
Okay, so relief is the geographic term for topography, just the physical jaggedness, the shape of the Earth's surface.
So mountains and valleys.
Yeah. Mountains act as colossal physical dams in the atmospheric ocean. When a wind system carrying moisture off the ocean collides with a mountain range, it obviously cannot pass through solid rock.
Right, so where does it go?
The air is forced violently upward. And as we just learned with altitude, ascending air expands and cools adiabatically.
And cold air has a lower capacity to hold water vapor.
You're getting it. So as the air gets shoved up the mountain, the water vapor condenses into clouds and unleashes massive precipitation on that front side.
That's the windward side.
Exactly. It's a mechanism called orographic lift.
So by the time that air mass reaches the very summit and begins to cascade down the back side of the mountain, it's been completely wrung out like a sponge.
Yes. And as that dry air descends the back of the mountain, the leeward side, it compresses and warms back up.
Wow.
This warm, bone-dry air creates what is known as a rain shadow, which is an area of extreme aridity.
Wow, so you can literally have a lush, vibrant rainforest on one side of a peak and a desolate, cracked desert just a few miles away on the leeward slope.
Exactly. It's all about which side of the rock you live on.
That mechanical understanding actually allows us to answer the text's bolded question. Why are most of the world's deserts located on the western margins of continents in the subtropics? It seems way too specific to just be a coincidence.
Oh, it's definitely not a coincidence. It is the flawless intersection of multiple climatic controls at
How
once.
so?
Well, in the subtropical latitudes, the dominant planetary winds are the trade winds, which blow from east to west.
Okay, east to west.
By the time these winds have traversed the massive expanse of an entire continent to reach the western margin, they have exhausted all their moisture. They are exceptionally dry offshore winds.
Oh, so they're blowing away from the land out to sea.
Right, and combine that with our fifth control, ocean currents. The western margins of continents typically feature cold ocean currents welling up from the deep.
And we know cold water chills the air above it.
Yes, creating dense, stable, high-pressure air that simply refuses to rise and form rain clouds. So you have dry winds blowing off the land and cold oceans suppressing any oceanic evaporation. The result, the Sahara, the Atacama, the Namib massive deserts sitting right on the western coast of their continents.
It's deeply satisfying to see the planetary physics just click together like that.
Right. It's like a giant clockwork mechanism.
So now the text zooms in, applying these 6 universal controls directly to the Indian subcontinent. It starts with latitude.
Let's hear it.
Factors affecting India's climate. Latitude. The Tropic of Cancer passes through the middle of the country from the Rann of Kutch in the west to Mizoram in the east. Almost half of the country lying south of the Tropic of Cancer belongs to the tropical area. All the remaining area north of the tropic lies in the subtropics. Therefore, India's climate has characteristics of tropical as well as subtropical climates.
Okay, so the Tropic of Cancer is an imaginary line at roughly 23.5 degrees north latitude. Geometrically, it marks the northernmost boundary on Earth where the sun can appear directly overhead at its absolute zenith.
So the sun is beating straight down on it.
Exactly. And the fact that this line bifurcates India, cuts it right in half, creates a sort of schizophrenic climatic baseline.
The bottom half and the top half are playing by different rules.
Completely. The southern half of the country is locked in the tropics, absorbing relentless direct solar radiation. The northern half sits in the subtropics, where the solar angle becomes a bit more oblique, introducing intense seasonal volatility.
But then we get to altitude, which seems to be the real geographic trump card.
Oh, absolutely.
The TAC reads, altitude. India has mountains to the north, which have an average height of about 6,000 meters. India also has a vast coastal area where the maximum elevation is about 30 meters. The Himalayas prevent the cold winds from Central Asia from entering the subcontinent. It is because of these mountains that this subcontinent experiences comparatively milder winters as compared to Central Asia.
6,000 meters, that is nearly 20,000 feet.
That is unimaginably huge.
Right, and we often think of mountains merely as, scenic backdrops. But atmospheric science demands we view them as functional infrastructure.
Like a wall.
Literally a 6,000-meter-high thermal fortress wall. Let's engage in a quick thought experiment. What if the Indian tectonic plate had never smashed into the Eurasian plate to create those mountains?
What would happen?
Well, during winter, the massive landmass of Siberia and Central Asia cools down incredibly fast, generating a colossal dome of heavy, freezing, high-pressure air.
Which wants to rush southward.
Exactly. Without the Himalayas, those brutal, freezing winds would cascade southward unimpeded, just flooding the entire Indian subcontinent.
Oh, wow. So the fertile plains of northern India would just freeze.
They would experience brutal, freezing winters. The agricultural foundation that supports hundreds of millions of people simply would not exist.
So the Himalayas act as a geological dam.
Yes, holding back an ocean of freezing air and artificially insulating India, giving it surprisingly mild winters compared to anywhere else at that latitude.
That geological luck sets the stage for the most complex physical mechanism in the text. We're moving from stationary geography to the fluid dynamics of a spinning planet.
This is where it gets really fun.
The text lays out the planetary wind systems. Pressure and winds. The climate and associated weather conditions in India are governed by the following atmospheric conditions: pressure and surface winds, upper air circulation, and western cyclonic disturbances and tropical cyclones.
Right, three main layers.
India lies in the region of northeasterly winds. These winds originate from the subtropical high-pressure belt of the northern hemisphere. They blow southwards, get deflected to the right due to the Coriolis force, and move towards the equatorial low-pressure area.
Okay, this section requires us to sort of zoom out to the edge of space to understand the planetary circulation.
Let's do it.
So the equator is hot, creating rising low-pressure air. The subtropics are relatively cooler, creating sinking high-pressure air. Naturally, as we know, the air wants to flow from the high-pressure subtropics down to the low-pressure equator to balance the ledger.
And these are the trade winds.
Exactly. And because India is located north of the equator, it sits squarely in the path of these winds blowing southward.
But the text introduces a crucial complication. It says they get deflected to the right due to the Coriolis force. It has a little definition box here.
Well, let's hear the definition.
Coriolis force, an apparent force caused by the Earth's rotation. The Coriolis force is responsible for deflecting winds towards the right in the northern hemisphere and towards the left in the southern hemisphere. This is also known as Farrell's law.
Okay, let's avoid simplistic analogies here and dig into the actual physics. Why does the wind curve just because the Earth is spinning?
Yeah, if I throw a ball, it doesn't just mysteriously curve right. Why does the wind?
It comes down to the conservation of angular momentum. Imagine the Earth spinning on its axis. A point on the equator has to travel roughly 24,000 miles in 24 hours to complete one rotation.
Okay, so it's moving fast.
Very fast. That means the land at the equator is spinning eastward at about 1,000 miles per hour. But as you move north toward the pole, the circumference of the Earth shrinks.
Right, the circle gets smaller.
So the land doesn't have to travel as far in 24 hours, so its rotational speed is much slower.
Like the inner versus outer lanes of a running track. The outside lane has to run faster to keep up.
That's a perfect analogy. Now imagine firing a long-range artillery shell or a massive wind system from the slower-moving north down toward the fast-moving equator.
Okay.
As the wind moves south, the Earth beneath it is rotating eastward faster and faster. So from the perspective of the ground, the wind appears to fall behind the rotation, curving off to the right.
Oh, so it's not the wind curving, it's the Earth spinning out from under it.
Exactly. That is the Coriolis force. It ensures that air moving south in the northern hemisphere becomes a northeasterly wind, meaning it's blowing from the northeast to the southwest.
Which sets up a profound paradox that the text points out. Generally, these winds carry little moisture as they originate and blow over land. Therefore, they bring little or no rain. Hence, India should have been an arid land, but it is not so. Let us see why.
It's a great cliffhanger.
It really is. If the planetary physics dictate that dry wind originating deep over the Asian landmass should constantly scour the subcontinent, why isn't India just a massive desert?
Because local thermodynamics can temporarily violently overpower planetary rotation.
It sounds intense. The text resolves the cliffhanger in the next paragraph, detailing what I guess we can call the Great Reversal. Let's read that reveal.
Go for it.
The pressure and wind conditions over India are unique. During winter, there is a high-pressure area north of the Himalayas. Cold, dry winds blow from this region to the low-pressure areas over the oceans to the south.
Okay, let's pause. This is the winter state, which follows the normal planetary rules we just established.
Right, the massive Asian landmass cools down, forming that dense high-pressure dome.
And the Indian Ocean to the south remains relatively warm, creating lower pressure. Air flows from high to low, meaning dry winds blow from the land out to the sea,
leaving India dry. But then, summer introduces a cataclysmic shift, the text says. In summer, a low-pressure area develops over interior Asia as well as over northwestern India. This causes a complete reversal of the direction of winds during summer.
This is the heartbeat of the monsoon. It is an annual thermodynamic coup d'etat.
The coup d'etat, how?
Well, as the Earth's orbit shifts the intense solar radiation northward into the Tropic of Cancer, the interior of Asia, particularly the vast, elevated Tibetan Plateau, begins to bake.
Like baking hot.
Think of the Tibetan Plateau as a colossal frying pan, hoisted thousands of meters into the atmosphere. It heats the air above it incredibly rapidly.
And hot air rises.
It surges upward. That scorchingly hot air violently surges into the upper atmosphere, leaving behind an atmospheric void and intensely powerful low-pressure vacuum at the surface.
I want to focus on the sheer power of that vacuum for a second. How strong does a thermal low have to be to essentially hijack the planetary wind system?
It is strong enough to reach across the entire hemisphere.
Wait, really?
Yes. At the exact same time Asia is baking, it is winter in the southern hemisphere. Down over the southern Indian Ocean, the air is cold, heavy, and sitting in a massive high-pressure zone.
Okay. High pressure south, massive vacuum north.
And the laws of fluid dynamics dictate that the high-pressure air must fill the low-pressure void. The Asian vacuum is so profound that it yanks that massive volume of air northward, completely overpowering the normal trade winds.
The text describes the path. Air moves from the high-pressure area over the southern Indian Ocean in a southeasterly direction, crosses the equator, and turns right towards the low-pressure areas over the Indian subcontinent. These are known as the southwest monsoon winds.
And as that air races northward, it has to cross the equator, which brings our friend the Coriolis force back into play.
Ah, because it changes hemispheres.
Exactly. The air starts in the southern hemisphere blowing northwest, but the second it crosses the equator into the northern hemisphere, Farrell's law asserts dominance.
So it hooks to the right.
Hard to the right. A wind that was blowing northwest is suddenly deflected so violently it begins blowing from the southwest toward the northeast. It becomes the southwest monsoon.
These winds blow over the warm oceans, gather moisture, and bring widespread rainfall over the mainland of India. That's the rest of the paragraph.
And crucially, the path that wind takes determines the fate of the subcontinent. Because it originates in the southern Indian Ocean, it travels thousands of miles across warm tropical waters.
So it acts like a sponge.
An immense sponge. It utilizes the thermal energy of the ocean to evaporate billions of tons of water into vapor. By the time that deflected, moisture-gorged wind collides with the Indian landmass, it is practically bursting.
So the intense heat of the Asian continent actually summons the waters from the sea.
Yes, that is exactly why India is not a desert.
It is an awe-inspiring mechanism. Okay, having mapped out the master planetary controls, the text now breaks down how this engine dictates the distinct seasonal realities on the ground.
The four seasons.
Right. It starts with the dry, cooler months. The seasons. The monsoon type of climate is characterized by a distinct seasonal pattern. The weather conditions greatly change from one season to the other. These changes are particularly noticeable in the interior parts of the country.
Continentality again.
The coastal areas do not experience much variation in temperature, though there is variation in rainfall pattern. How many seasons are experienced in your place? 4 main seasons can be identified in India: the cold weather season, the hot weather season, the advancing monsoon, and the retreating monsoon, with some regional variations.
Let's start with winter.
The cold weather season, winter. The cold weather season begins from mid-November in northern India and stays till February. December and January are the coldest months in the northern part of India. The temperature decreases from south to the north.
Notice how the text is constantly reaffirming the structural controls we established earlier. The temperature decreases from south to north, that is the latitude control at work.
And it gives data. The average temperature of Chennai on the eastern coast is between 24 degrees to 25 degrees Celsius, while in the northern plains, it ranges between 10 degrees and 15 degrees Celsius.
Right. Chennai on the coast stays at a balmy 25 degrees due to continentality, while the northern plains drop down to 10 degrees.
Days are warm and nights are cold. Frost is common in the north, and the higher slopes of the Himalayas experience snowfall. During this season, the northeast trade winds prevail over the country.
The northeast trade winds have reclaimed dominance because the massive thermal vacuum of summer has collapsed.
They blow from land to sea, and hence, for most part of the country, it is a dry season.
Right. The winds are blowing from the dry Asian landmass out to the sea, which leads to clear skies, low humidity, and a total lack of widespread precipitation.
But geography throws a curveball. The text says some amount of rainfall occurs on the Tamil Nadu coast from these winds, as here they blow from sea to land.
That is a phenomenal geographic quirk.
How does that work if the wind is blowing away from the land?
Well, as the dry northeasterly winds sweep down across the eastern edge of the subcontinent, a portion of that air mass moves out over the Bay of Bengal.
Okay, so it leaves the land and goes over water.
Yes. And as it passes over the water, it picks up oceanic moisture. The curvature of the coastline means that when the wind continues its southward trajectory, it actually slams back into the Indian landmass, specifically at the Tamil Nadu coast.
Oh, so it hooks back around.
Basically, yes. Because that localized wind has just come off the water, it dumps rain. So Tamil Nadu experiences its peak rainfall while the rest of the country is bone dry.
That's fascinating. But there's another vital anomaly in the winter section. The text reads, In the northern part of the country, a feeble high-pressure region develops, with light winds moving outwards from this area. Influenced by the relief, these winds blow through the Ganga Valley from the west and the northwest. The weather is normally marked by clear sky, low temperatures, and low humidity and feeble variable winds. But then it says, a characteristic feature of the cold weather season over the northern plains is the inflow of cyclonic disturbances from the west and the northwest. These low-pressure systems originate over the Mediterranean Sea and Western Asia and move into India, along with the westerly flow.
Okay, this is amazing.
How on earth does a storm system travel from the Mediterranean Sea across Europe and the Middle East to drop rain on northern India?
It requires an upper atmospheric conveyor belt. We are shifting from surface winds to upper air circulation here.
Okay, what's up there?
Approximately 10,000 to 12,000 meters above sea level, there are narrow bands of incredibly fast-moving wind known as the subtropical westerly jet streams.
Like the jet stream you hear about on the news.
Exactly. These jet streams roar from west to east at speeds exceeding 100 miles per hour. During winter, extratropical cyclones, which are basically low-pressure storm systems, develop over the Mediterranean Sea.
And the jet stream catches them.
The jet stream essentially catches these storm systems and violently drags them thousands of miles eastward across Iran, Afghanistan, and Pakistan, eventually depositing them right over the northern plains of India.
That is incredible. The text notes, they cause the much-needed winter rains over the plains and snowfall in the mountains. Although the total amount of winter rainfall, locally known as mahawat, is small, they are of immense importance for the cultivation of rabi crops.
This is where atmospheric physics intersects with human survival.
How so?
Rabi crops like wheat, barley, and mustard are sown in the winter. Now, the northern plains are inherently dry during this season due to the land-to-sea wind pattern we talked about.
So they wouldn't get any water normally.
None. If that Mediterranean storm system fails to reach India via the jet stream, the wheat crop receives no moisture at its most critical germination phase. The yield collapses, triggering severe agricultural and economic distress.
So millions of livelihoods depend entirely on the reliability of a high-altitude wind carrying a storm from the coast of Italy.
It's a remarkably precarious dependency.
And the text finishes the winter section saying, the peninsular region does not have a well-defined cold season. There is hardly any noticeable seasonal change in temperature pattern during winters due to the moderating influence of the sea.
Continentality strikes again.
Always. Okay, so as winter fades, the orbital mechanics of the planet drag the heat back toward the north, initiating a brutal transition.
Summer.
The hot weather season.
Yeah.
Summer. Due to the apparent northward movement of the sun, the global heat belt shifts northwards. As such, from March to May, it is hot weather season in India.
Just to clarify, the phrasing apparent northward movement of the sun is key. The sun isn't actually moving, of course.
Right, we're orbiting it.
The Earth's axial tilt causes the zone of maximum solar radiation to march steadily north from the equator toward the Tropic of Cancer between March and May.
And you can track the heat wave moving through the data the text provides. It says, the influence of the shifting of the heat belt can be seen clearly from temperature recordings taken during March-May at different latitudes. In March, the highest temperature is about 38 degrees Celsius, recorded on the Deccan Plateau. In April, temperatures in Gujarat and Madhya Pradesh are around 42 degrees Celsius. In May, temperature of 45 degrees Celsius is common in the northwestern parts of the country. In peninsular India, temperatures remain lower due to the moderating influence of the oceans.
So you see it moving. 38 degrees in the central plateau in March, 42 degrees further north in April, and 45 degrees in the northwest by May.
And that escalating heat is what starts carving out that massive low-pressure vacuum we discussed earlier.
Yes.
But before the monsoon arrives to fill that void, the thermodynamics on the ground turn. Well, lethal. The text describes a phenomenon. The summer months experience rising temperature and falling air pressure in the northern part of the country. Towards the end of May, an elongated low-pressure area develops. Circulation of air begins to set in around this trough. A striking feature of the hot weather season is the loo. These are strong, gusty, hot, dry winds blowing during the day over the north and northwestern India. Sometimes they even continue until late in the evening. Direct exposure to these winds may even prove to be fatal.
Okay, let's dig into why dry heat combined with wind is so catastrophic for human physiology.
Because usually, a breeze cools you down.
Usually, yes. It has to do with the wet bulb temperature and the mechanics of human sweat. The human body cools itself through the evaporation of sweat, which pulls latent heat away from the skin.
Right.
Now, the Lu originates in the scorching deserts of the Northwest. It is superheated to 45 degrees Celsius over 110 Fahrenheit and possesses almost zero humidity.
So it's basically a hairdryer.
Exactly like a hairdryer. When a high-velocity 45-degree wind hits a human body, it rapidly accelerates dehydration. The dry air evaporates sweat faster than the body can actually produce it,
Oh, wow.
meaning the body's internal cooling mechanism is completely overpowered by the relentless kinetic transfer of heat from the wind. Your core body temperature spikes, leading to rapid heat stroke and, as the text notes, fatality.
That is terrifying. In that context, the next line is deeply counterintuitive.
Hmm.
The text says, dust storms are very common during the month of May in northern India. These storms bring temporary relief as they lower the temperature and may bring light rain and cool breeze.
I know, it sounds crazy.
How does a blinding storm of dirt lower the temperature?
A dust storm acts as a massive airborne solar shield.
A shield?
Yes. The intense heat of the ground creates violent, localized updrafts that tear topsoil from the dry earth, blasting it high into the troposphere. This suspended particulate matter, the dust actually intercepts and reflects incoming solar radiation back into space.
Oh, so it's blocking the sun.
The ground below is suddenly cast into deep shade, which can drop the ambient temperature by several degrees almost instantaneously. Furthermore, these updrafts occasionally possess enough energy to puncture the inversion layer and access high-altitude moisture, triggering isolated, highly localized rain showers before the moisture instantly evaporates again.
So a dirt storm is basically temporary AC. The atmosphere is just reaching a boiling point here. The text goes on. This is also the season for localized thunderstorms, associated with violent winds, torrential downpours, often accompanied by hail.
Yeah.
In West Bengal, these storms are known as the Kal Baisakhi.
The air is intensely hot and highly unstable. In the east, where there is slightly more moisture available from the Bay of Bengal, the extreme surface heating triggers explosive convection.
Explosive convection.
Warm, moist air rockets upward, freezes at high altitudes, and collapses back down as violent squalls and hail. The name Kal Baisakhi literally translates to the calamity of the month of Baisak due to the devastation these storms wreak on crops and infrastructure.
It's also violent, but the text contrasts that with the South. Towards the close of the summer season, pre-monsoon showers are common, especially in Kerala and Karnataka. They help in the early ripening of mangoes and are often referred to as mango showers.
Because in the south, the proximity to the ocean moderates the violence. So you get gentle pre-monsoon showers that perfectly coincide with the maturation of the mango crop.
A nice reprieve. But all of this chaos, the Lu, the dust storms, the mango showers, it's simply the overture.
The main event is coming.
The low-pressure vacuum has reached its maximum intensity, and the planetary winds are about to answer the call. The text moves to the main event. Advancing monsoon, the rainy season.
We know.
By early June, the low-pressure condition over the northern plains intensifies. It attracts the trade winds of the southern hemisphere. These southeast trade winds originate over the warm subtropical areas of the southern oceans. They cross the equator and blow in a southwesterly direction, entering the Indian Peninsula as the southwest monsoon.
So June marks the kinetic culmination of the great reversal we talked about earlier. The vacuum is established, the Coriolis force deflects the southern winds to the right, and millions of tons of evaporated Indian Ocean water collide with the subcontinent.
As these winds blow over warm oceans, they bring abundant moisture to the subcontinent. These winds are strong and blow at an average velocity of 30 kilometers per hour. With the exception of the extreme northwest, the monsoon winds cover the country in about a month.
30 kilometers per hour is a solid, relentless push of water and wind.
The inflow of the southwest monsoon into India brings about a total change in the weather. Early in the season, the windward side of the Western Ghats receives very heavy rainfall, more than 250 centimeters. The Deccan Plateau and parts of Madhya Pradesh also receive some amount of rain in spite of lying in the rain shadow area.
And exactly where that water falls is dictated flawlessly by the geographic relief controls we mapped earlier. The windward side of the Western Ghats gets blasted. The winds hit the mountain barrier, rise, cool adiabatically, and dump their moisture.
While the Deccan Plateau sits immediately behind those mountains in the rain shadow, receiving a fraction of the moisture.
Exactly.
But let's look at the absolute extreme. The text declares the maximum rainfall of this season is received in the northeastern part of the country. Masinram, in the southern ranges of the Khasi Hills, receives the highest average rainfall in the world.
The highest in the world.
What makes the geography there so uniquely efficient at extracting water from the sky?
It is an unparalleled geographic funnel. The Khasi Hills feature deep, steep-sided valleys that open directly southward, facing the Bay of Bengal.
Okay, so they're like giant catcher's mitts.
Yes. As the moisture-laden monsoon winds sweep northward off the warm ocean, they are channeled directly into these narrow valleys. The topography forces the air mass upward at a terrifyingly rapid velocity.
And extreme upward movement means extreme cooling.
The extreme adiabatic cooling triggers near-continuous torrential condensation. It is the perfect atmospheric choke point, wringing the clouds out like a sponge and resulting in that incomprehensible 13 feet of annual rainfall.
13 feet, that's just wild. The text then says, rainfall in the Ganga Valley decreases from the east to the west. Rajasthan and parts of Gujarat get scanty rainfall.
Because the wind is drying out as it moves.
Right. But then the text pivots from predictable geography to chaotic fluid dynamics. This might be the most crucial part of this section. It says, another phenomenon associated with the monsoon is its tendency to have breaks in rainfall. Thus, it has wet and dry spells. In other words, the monsoon rains take place only for a few days at a time. They are interspersed with rainless intervals.
This is so important. The monsoon isn't just a constant, predictable fire hose of water.
These breaks in monsoon are related to the movement of the monsoon trough. For various reasons, the trough and its axis keep on moving northward or southward, which determines the spatial distribution of rainfall.
Okay, what exactly is this trough?
Yeah, please explain that.
Imagine the monsoon trough as a massive, invisible magnetic line hovering in the atmosphere over India. It represents the absolute deepest valley of low pressure within that larger vacuum we discussed.
So it's the core of the vacuum.
Exactly. Because moisture is drawn to the lowest pressure, the heaviest rain clouds constantly seek out and follow the axis of this trough.
So wherever the trough goes, the rain goes.
Yes. However, atmospheric fluid dynamics are incredibly chaotic, heavily influenced by global upper air waves known as Rossby waves. These waves cause the trough to wobble unpredictably north and south throughout the season.
And the socioeconomic consequences of that wobble are catastrophic. The text says, when the axis of the monsoon trough lies over the plains, rainfall is good in these parts. On the other hand, whenever the axis shifts closer to the Himalayas, there are longer dry spells in the plains, and widespread rain occur in the mountainous catchment areas of the Himalayan rivers.
Consider the devastating irony of that mechanism.
These heavy rains bring in their wake devastating floods causing damage to life and property in the plains.
Right. When the trough shifts to the mountains, the farmers in the plains experience a break, a dry spell under the scorching sun. Their crops begin to wither, threatening severe agricultural drought.
But wait, if they're having a drought, where's the flood coming from?
From the mountains. Unimaginable volumes of water are pouring into the high-altitude Himalayan river basins because the trough moved there. That water is governed by gravity, eventually surges down the Ganges and Brahmaputra river systems, blasting back into the plains.
Oh, so the farmers who were just suffering from a drought suddenly find their fields submerged beneath devastating floods.
Yes, you can have a drought and a flood destroy the exact same region within a 3-week window, entirely dependent on how an invisible pressure trough wobbles in the atmosphere.
The text finishes this section by summarizing exactly that. The frequency and intensity of tropical depressions, too, determine the amount and duration of monsoon rains. The monsoon is known for its uncertainties. The alternation of dry and wet spells vary in intensity, frequency, and duration. While it causes heavy floods in one part, it may be responsible for droughts in the other. It is often irregular in its arrival and its retreat. Hence, it sometimes disturbs the farming schedule of millions of farmers all over the country.
It really highlights how deeply precarious the agricultural foundation of a billion people truly is.
Eventually, however, the vacuum begins to collapse.
The retreat.
The text moves to the transition. Retreating post-monsoons, the transition season. During October-November, with the apparent movement of the sun towards the south, the monsoon trough, or the low-pressure trough over the northern plains, becomes weaker. This is gradually replaced by a high-pressure system.
So the engine is powering down. As the Earth continues its orbit, the intense solar radiation shifts back south toward the equator.
The southwest monsoon winds weaken and start withdrawing gradually. By the beginning of October, the monsoon withdraws from the northern plains.
Without that extreme heat, the Asian landmass begins to cool, and the massive low-pressure vacuum loses its grip. The heavy, high-pressure air begins to reassert dominance, pushing the southwest monsoon winds back toward the sea.
The months of October-November form a period of transition from hot rainy season to dry winter conditions. The retreat of the monsoon is marked by clear skies and rise in temperature. While day temperatures are high, nights are cool and pleasant. The land is still moist.
which creates a unique problem.
Right. Owing to the conditions of high temperature and humidity, the weather becomes rather oppressive during the day. This is commonly known as October heat.
So before the cool, dry winter fully sets in, you get this miserable micro season.
Why does clear skies and moist land create such oppressive conditions?
It is an extreme manifestation of latent heat and humidity. When the rain clouds clear, intense solar radiation strikes the ground that is essentially a massive sponge saturated with 4 months of water.
Which causes immense evaporation.
Yes. However, because the air is now stagnant, the winds have weakened, the humidity levels just spike drastically. Returning to human physiology, high ambient temperature combined with near total humidity means sweat cannot evaporate from the skin.
So you can't cool down.
The body loses its ability to shed thermal energy, making the heat feel suffocating and oppressive, even if the absolute temperature is lower than it was in May.
Just sticky and miserable. The other hallmark of this transition period is raw destruction on the eastern coast.
Yes, the cyclones.
The text reads, "In the second half of October, the mercury begins to fall rapidly in northern India. The low-pressure conditions over northwestern India get transferred to the Bay of Bengal by early November. This shift is associated with the occurrence of cyclonic depressions, which originate over the Andaman Sea.
Mm.
These cyclones generally cross the eastern coast of India, cause heavy and widespread rain. These tropical cyclones are often very destructive. The thickly populated deltas of the Godavari, the Krishna, and the Kaveri are frequently struck by cyclones, which cause great damage to life and property. Sometimes these cyclones arrive at the coasts of Odisha, West Bengal, and Bangladesh. The bulk of the rainfall of the Coromandel Coast is derived from depressions and cyclones."
So the low-pressure trough shifts over the water of the Bay of Bengal, spawning destructive tropical cyclones. Why do they form specifically during this retreating phase?
Yeah, why November?
Cyclogenesis, the formation of cyclones, requires immense thermal energy from the ocean surface. By November, the Bay of Bengal has spent the entire summer absorbing intense heat. The water is exceptionally warm.
And the low-pressure trough moves over it.
Yes, and acts as an ignition switch. Warm, moist air rises rapidly in a massive spiral driven by the Coriolis force. As that rising moisture condenses into rain, it releases latent heat, which further fuels the storm's updraft.
It becomes a self-sustaining engine.
A runaway thermal engine. Because the prevailing wind patterns are shifting back toward the southwest, these massive storms are steered directly into the thickly populated, low-lying agricultural deltas of the eastern coast, bringing catastrophic wind shear and storm surges.
Yet, as the text points out, the bulk of the rainfall for the Coromandel Coast comes from these destructive depressions. The very mechanism that destroys lives is also the primary mechanism delivering the water required to sustain them.
It is a brutal geographic paradox.
We're now moving into the final sections of the main text, which offer a quantitative summary and a profound philosophical conclusion.
Let's read it.
Distribution of rainfall. Parts of western coast and northeastern India receive over about 400 centimeters of rainfall annually. However, it is less than 60 centimeters in western Rajasthan and adjoining parts of Gujarat, Haryana, and Punjab. Rainfall is equally low in the interior of the Deccan Plateau and east of the Sayadris.
The rainfall distribution summary here just confirms everything we've established about geographic controls. The windward coasts and funneled valleys of the northeast get inundated with 400 centimeters of water.
Why do these regions receive low rainfall? A third area of low precipitation is around Leh in Jammu and Kashmir. The rest of the country receives moderate rainfall. Snowfall is restricted to the Himalayan region.
Right, the leeward rain shadows of the Deccan Plateau and the western margins of Rajasthan are starved of moisture. And Leh, sitting at extreme altitude behind the Himalayan barrier, is a cold, dry desert. The physics are remarkably consistent.
Owing to the nature of monsoons, the annual rainfall is highly variable from year to year. Variability is high in the regions of low rainfall, such as parts of Rajasthan, Gujarat, and the leeward side of the Western Ghats. As such, while areas of high rainfall are liable to be affected by floods, areas of low rainfall are drought-prone.
It all tracks perfectly.
But I am really struck by how the text pivots now from raw, uncaring meteorological data to the concept of the monsoon as a unifying bond. India is a subcontinent defined by its fractures, wildly different languages, cultures, cuisines, and geographies.
Yet every single one of those cultures is synchronized to the exact same atmospheric pressure system.
Let's read this final section. Monsoon as a unifying bond. You have already known the way the Himalayas protect the subcontinent from extremely cold winds from Central Asia. This enables northern India to have uniformly higher temperatures compared to other areas on the same latitudes. Similarly, the peninsular plateau, under the influence of the sea from three sides, has moderate temperatures. Despite such moderating influences, there are great variations in the temperature conditions. Nevertheless, the unifying influence of the monsoon on the Indian subcontinent is quite perceptible.
The text beautifully outlines how the flora, the fauna, and the agricultural calendar all revolve around the breath of the planet.
The seasonal alteration of the wind systems and the associated weather conditions provide a rhythmic cycle of seasons. Even the uncertainties of rain and uneven distribution are very much typical of the monsoons. The Indian landscape, its animal and plant life, its entire agricultural calendar, and the life of the people, including their festivities, revolve around this phenomenon.
When the Tibetan Plateau heats up and the Coriolis force yanks the winds across the equator, 1 billion people collectively look to the sky.
Year after year, people of India from north to south and from east to west eagerly await the arrival of the monsoon. These monsoon winds brine the whole country by providing water to set the agricultural activities in motion. The river valleys which carry this water also unite as a single river valley unit.
The festivals celebrating the sowing of seeds, the rituals marking the harvest, the economic planning of the government, they are all human reactions to fluid dynamics. The river valleys act as the circulatory system for this water, uniting different states as a single hydrological unit.
It makes you realize that we often view nature as a backdrop to human history, but in reality, atmospheric physics is the very stage upon which human culture is constructed.
Beautifully said.
Now, to truly master this material, our mission requires us to look at the practical exercises and data the text provides at the end of the chapter. We promise we are not going to skip any part of the source.
We did promise. Let's do it.
The text presents multiple choice questions, which we will use as springboards to test the mechanisms we just decoded. It reads, 1. Choose the correct answer from the 4 alternatives given below. Which one of the following places receives the highest rainfall in the world? A. Silchar, B. Mount Sinram, C. Cherrapunji, D. Guwahati.
Based on the structural controls we analyzed, the answer is unequivocally B. Masinram.
And we know why, right?
Yes. We know it isn't just about being in the path of the monsoon, it is about the microgeography. Masinram is nestled in the southern Kazi Hills, where the funnel-shaped valleys force the saturated ocean winds upward at a velocity that maximizes adiabatic cooling and condensation, wringing out the highest volume of water on the planet.
Perfect. The next question reads, the wind blowing in the northern plains in summers is known as A. Kawaisaki, B. Lu, C. Trade winds, D. None of the above.
We can deduce this by eliminating the others based on their thermodynamic properties. Trade winds are planetary. They don't exclusively define the brutal summer plains. Kawaisaki are the violent thunderstorms triggered by instability in West Bengal.
So it's the Lu.
The answer is B. Lu, the hot, dry, gusty wind that causes lethal spikes in wet bulb temperatures by completely overpowering the human body's evaporative cooling mechanisms.
Got it. Question 3. Monsoon arrives in India approximately in A. Early May, B. Early July, C. Early June, D. Early August.
This tests the timing of the Great Reversal. The intense solar heating peaks in May, creating the low-pressure vacuum.
And then it takes a minute for the vacuum to work.
Right. It takes until C, early June, for that vacuum to generate enough kinetic pull to yank the high-pressure air from the southern hemisphere across the equator.
And the final multiple choice. 4. Which one of the following characterizes the cold weather season in India? A. Warm days and warm nights. B. Warm days and cold nights. C. Cool days and cold nights. D. Cold days and warm nights.
Again, refer back to the physics of humidity and radiation. During winter, the winds blow from the dry land mass to the sea. The lack of atmospheric moisture means there is no greenhouse blanket to trap heat.
So the sun works during the day, but at night.
During the day, solar radiation warms the land efficiently. But at night, that heat escapes instantly into space. The result is B, warm days and cold nights.
Excellent. To conclude, the text provides a data set labeled Table 1, showing the average monthly temperature and rainfall for various cities. We won't read every single number, but we must analyze the stark thermodynamic realities the data reveals. For instance, look at the contrast between Mumbai and Leh in July. Mumbai receives 61 centimeters of rain in that single month. Leh receives 1.3 centimeters.
The data mathematically validates our geographic models. Mumbai sits on the windward coast of the Western Ghats, directly intercepting the moisture-gorged southwest monsoon winds off the Arabian Sea. The orographic lift forces massive precipitation.
And Leh.
Leh, however, is located in the Trans-Himalayan region at an altitude of over 3,500 meters. The towering Himalayan ranges completely strip the monsoon winds of all moisture before they ever reach Leh, leaving it a frozen, high-altitude desert.
Let's examine another data contrast the text hints at. Delhi versus Jodhpur. Delhi receives 67 centimeters of rain annually, while Jodhpur receives only 36.6 centimeters. They're relatively close geographically, so why the disparity?
You just have to trace the trajectory of the wind. The monsoon branch that strikes the Bay of Bengal is deflected northwestward by the Himalayas, funneling up the Ganga Valley toward Delhi.
Dropping moisture along the way.
Exactly. It drops moisture steadily along that path. Jodhpur is located further west in Rajasthan. By the time that specific wind system reaches Jodhpur, it has traveled over hundreds of miles of hot land, dropping its moisture continuously.
So it's just empty by the time it gets there.
The air mass is practically desiccated by the time it arrives. The data perfectly maps the exhaustion of the wind's moisture supply.
One final data point. Thiruvananthapuram shows a staggering lack of temperature variance. It hovers around 26 to 27 degrees Celsius every single month of the year.
The ultimate proof of continentality. Located at the extreme southern tip of the peninsula, it is surrounded by the immense thermal mass of the Indian Ocean, which utterly nullifies any seasonal extreme, locking the temperature into a state of perpetual equilibrium.
We set out on a massive mission today. We took a dense geographic text, read every single word, and decoded the complex machinery beneath it. We moved past the simple ideas of hot and rainy to understand adiabatic cooling, specific heat capacity, the conservation of angular momentum causing the Coriolis force, and the thermodynamic vacuum that pulls an ocean of water across the equator.
We covered a lot of ground.
We saw how a 6,000-meter wall of rock shaped human history, and how a distant storm over the Mediterranean feeds winter crops thousands of miles away.
The text reveals that the Earth is not a static backdrop, but a delicately balanced, highly reactive engine.
But I want to leave you with a final thought to ponder that builds on the text we just mastered. We spent this entire deep dive learning the exact rules, temperatures, and pressures required to operate this planetary engine. We learned how an entire subcontinent's agriculture, economy, and culture are precariously balanced on the precise wobble of a monsoon trough and the predictable shifting of global heat belts. So, consider the thermodynamics. What happens to this ancient rhythm as global temperatures begin to subtly shift the baseline data?
That's the terrifying part.
If the Asian vacuum gets hotter, or the Indian Ocean absorbs more thermal energy, how will the chaotic fluid dynamics of the trough respond? How will a billion people adapt when the very schedule and intensity of that unifying bond begins to change its fundamental physics?
It is the defining geographic question of the century.
Thank you so much for joining us on this deep dive. Next time you feel a drop of rain, remember the invisible planetary machinery pulling it across the sky. Keep questioning the world around you.